Studying the stability of compounds at a conjugated cyclic planar is something that Hickel did. And now we know that Hickel rules for aromatic compounds says that the compounds to be aromatic, they need to be fully conjugated, cyclic, planar, and have 4n plus 2 pi electrons. Now, in anti-aromatics would be conjugated, cyclic, planar, but do not have 4n plus 2 pi electrons, where n is an integer. Now, we were placing electrons in molecular orbitals that were formed in the pi system. Here we were doing molecular orbital of the pi system. And these are built, the molecular, the MOs, are built from atomic orbitals, the p orbitals in the pi system. But there is a tool to learn how to replace in the relative energies those MOs. And this is closed circles. And so what it is, I'm going to try to draw that the best that I can. Let's see what happens. But I'm going to say I'm going to cheat a little bit here, because I'm going to draw a structure of several polygons. And now let's do, this is a pentagon, right? And so what we do in the first circle is that we will put a polygon inside a circle. So but I know that I did first the polygon, but it's easier. It's kind of hard to draw it. This is wrong, actually. I'm going to redraw it, but that makes, it's a good idea so that to stress the point that to use this tool, we need to draw the polygon with one vertex down. So now I am going to draw a circle. Well, it came out a little larger. Okay, not perfect, but all right. So what we need to do now is where the circle cuts is in contact with the polygon, we're going to draw a line, and this will represent the energy level of the MOs. And voila, here we have the diagram of energy level of the MOs of cyclo. Say that we were doing this if we wanted to explain MO energy levels of cyclobutadiene. And that for benzene. And here, by the way, this will be, say, my 0 energy. Now that's the center of that. And my energy levels will be here, where it say is in contact with the circle. And as you can see, I have 3 orbitals that are lowered in energy. These are the 3 bonding, the 3 lines that are here. Is the 3 bonding MOs. Bonding that we used in a previous video, and these are the 3 anti-bonding, just 3 so above that line in the center. So these are anti-bonding. We don't have anything in this line in the center at the same, say, energy level of the p orbital. So nothing that is non-bonding. Here we have 2 non-bonding, bonding, anti-bonding. And for the, if we had a polygon such as that, in, say that I want to explain the cyclo and the dianyl anion, that anion. So to see the energy levels, then I will draw that polygon inside the circle, and then I will do the following. So here the line goes about that, and we will have 3 bonding molecular orbitals, 3 bonding MO, into anti-bonding. And all we need to do, if we need to do the electron configuration here, is now to place the electrons in the orbital. Say that I was studying this, so cyclopentadiene, so we have 4 pi electrons, so I'm placing 1, 2, and then Hans rule, 3, 4. So open shell configuration, not everything is paired up, so not as stable. When we did a benzene, if you do benzene, is 2, 4, 6 pi electrons, and you do the same, place them from the bottom up, Aufbau principle to here, Hans rule here, and then you complete the 6 electrons, Pauli's exclusion principle. Everything is paired up in all the electrons in the involving MO, so, and that's closed shell, so stable. Closed shell configuration. This is open shell, actually. Note everything is paired up. And if we see there's anion, cyclopentadienyl anion, so we have 2, 4, 6 pi electrons, 6 pi electrons. And the carbon right here, notice that it is next to a double bond. So it is at an allylic position. So it's also sp2 hybridized. So everything is sp2 hybridized. So it's fully conjugated. And it's cyclic, it's planar. And we are going to place now the 6 pi electrons here. So at the lower energy level, put this 2. And then we have 6. So 4, 5, and 6. So it is also closed shell configuration. And so that is stable. So this anion is aromatic. And so here we're using first circle. You can do this for a larger size polygon. But always remember that we need to put the polygon inside a circle, but with one vertex down. And so when it cuts the circle, it gives you the energy level of the molecular orbital. Then you place pi electrons from the bottom up, complying with the rules when you do electron configurations.